You guys can see the video, okay?
Yeah.
Okay.
Yes.
All right. Good. I just want to make sure everything's okay. So, I want to talk about the second to last lab of the semester, and I'm going to have to change. I might have to modify the due date for that one too. And I don't have the microphone hooked up because I have a second camera connected. And you can see the second camera, so we can look at circuit. So this lab, this experiment is on RC circuit. And we covered RC circuits earlier, RL circuits. And I will talk about the RLC circuit. There's 3 parts to this lab, and I had to eliminate the last part. And the reason being is the inductor does not allow you to observe what I expect you to observe. Okay, so that was our fault. And so the last part, all I wanted you to do is to set up a circuit that exhibited the physical phenomenon. And then you would just take a picture of it and that's it. But because of the fact that the inductor is too small, we can't do it. Okay, so you're only doing the first 2 parts of the lab. And really the focus on this lab is, again, using the scope and doing some basic wiring. Okay, so let's go back and let's talk about the RC circuit. RC circuit, you basically have a power supply, and in this lab we're not going to use a DC power supply. We're going to use a power supply that varies with time, because otherwise looking at the signal of the scope would be very boring. So we'll use a power supply that's a square pulse. Okay. And we'll have a resistor and a capacitor. And you're going to hook up a scope to measure the voltage across the capacitor. And if you remember, the voltage across the capacitor looks like this. We want to test this equation. We want to test this equation by measuring the voltage across the capacitor at a certain instant in time. There's a lot of ways we can actually verify this equation, but I want to verify it in this manner because it focuses on your ability to be able to use the scope. Okay, that's the reason why we're doing it this way. I mean,
Sorry, Professor.
Yeah.
We can't see the right side of the board. It's kind of like...
Oh, okay. Thank you. Thanks for letting me know. Okay, let me fix that. Well, thanks for reminding me. I should look in the camera. I think I'm zooming in too much. Is that better?
Yeah, that's better. That's better.
Okay, cool. Thank you. So, really, I'm going to focus on basically using the scope. We could measure V as a function of time with the properly chosen values of R and C, but I don't want to do that. Our goal is to focus on the scope. And so what we're going to do is this. We're going to measure how long it takes for delta V sub C to be equal to 1/2 the power supply voltage. We're going to call this T1/2. We're going to determine the T1/2, and then we can do that on the scope. All you got to do is measure the power supply voltage, okay, or just measure the maximum voltage, and then measure how much time it takes to get to half the value using your scope. Okay. And what I've set up, and what you see is I've actually set up a RL circuit. What you see in the diagram, and I have the scope set up for that. And I'll play around with it so you can give you some ideas of what you can do to get good measurements. So you'll set this up, and then we're going to be able to calculate C if we know R. So let's assume that, and this is the theory section, by the way, in your lab. In your lab, you're going to be expected to derive this. You're not going to derive it from scratch. You start from here. Okay? You start from here and then carry out your derivation. So let's let this be half of that. Well, this thing ends up being a half, so I can cancel out the delta p's. And if I do some more math, I'll get 1/2 equals e to the minus t 1/2 over RC. Take the log of both sides. And then I can flip this. Cancel out the minus signs, and then solve for C. Everyone see that?
Yeah, why? Sorry, why is it t over 2 again?
But this one?
Yeah.
It's just a label.
Oh, it's just like, oh, it's t at time. Oh, time at 1/2. Okay, I get it.
Yeah, it's t. We when at the time at which the voltage is 1/2 its maximum value is usually
That's that time. Okay.
t 1/2. So what you're going to do is you're going to measure the time it takes for the voltage to get 1/2 its maximum value, and you're going to measure the resistance, and you're going to calculate this. So you will be doing error propagation because you're going to estimate the uncertainty of this number and this number, and you'll do this one for 3 frequencies. Okay, you'll do it for 3 frequencies. And the question is, does the frequency make a difference? Right. Or is it how fast the signal drops that makes a difference in your ability to measure this on the scope? Okay. I guess the question: what are the limitations of this measurement? How can I make the measurement better? Those are things you want to think about. Okay. When you do it at 3 different frequencies, there's one better than the other. Okay, so you'll adjust this, you'll do 3 different frequencies for this, and you'll only use in part 1. The second part, when we do the RL circuit, you'll only do it 1 frequency. Really, that's it for the measurement, for part 1. There's one part that we normally do that I had to take out because we can't do it with this scope. The scope doesn't have a feature. Most oscilloscopes have a feature where you pull out a button and it expands the horizontal scale by a factor of 10. If you look at the trace on the oscilloscope that you see in the bottom left-hand corner, you can actually measure the slope at t equals 0. You can actually calculate dv dt and then plug in t equals 0. You can measure the slope at t equals 0 on the scope. Not this one, okay? Not this particular one, but the ones we do in class, we can do that. And from there, we can also determine C. Okay. Questions? So in part 2, all we're going to do is we're going to change the capacitor with an inductor. Okay, you'll just replace the capacitor with an inductor. Now the question is, what does the inductor look like? Okay, the inductor looks like a big resistor. It's brown. I'll show you what the inductor looks like when I show you the circuit. So in part 2, we're going to do the same thing. Now the voltage across the inductor, what does that look like? Now we've done this, let's talk about this. Well, the current in the circuit with an inductor looks like this. I don't know if anybody noticed, but last week, after lunch, I wrote this equation on the board. And I didn't notice, nobody noticed, that this was flipped on the board. So when you look at the video, this equation is incorrect. It's flipped. In fact, when I put the video on YouTube, I actually made a note of it. Okay. All right. So we're going to measure delta V sub. So how do I find the voltage across the inductor? Well, the voltage across the inductor is L di over dt. And so if you take the derivative of this with respect to time, this is a constant, and then multiply by L, you will get the following. By the way, if you have a hard time doing this for the inductor when you make the measurements, then just do the resistor. Sometimes the inductor could be a pain. In fact, what I have set up here, I actually have it hooked up across the resistor. I'll show you the difference. I'll hook it up across the inductor so you can see the difference. But the equation you'll use is the same. As I go through this, you got to remember there's a theory section where I have to derive this equation using math type and all that fun stuff. Okay, so again, I want to measure when delta V sub L is 1/2 the power supply voltage. So I want this to be 1/2 delta V. And again, I get 1/2, same thing. I take a log of both sides. And then I flip it over. Oh, this is 1/2, sorry. I flip this 2 over. And then I solve for L. So what is L? This is like 1/2. So L is going to be R times T 1/2 over the natural log of C. Okay, so the inductor you're given, the given inductor, is 1.0 millihenries. I wish it would have been 10 millihenries because then we could do part 3. Okay, but it's 1 millihenry. All right, so this is the So this is the labeled value. There's a color code for it, but don't worry about knowing the color code for this here. Okay, but there's a color code for it. It's the color is it's black. I'm sorry, it's brown, black, red, gold. Okay. The inductor that comes in your kit looks exactly like a resistor. It just looks like a big resistor. Okay. So this one looks like a big resistor. It's brown, black, the color code, red, gold. That way you can identify it. Okay? And so, same thing again, you'll measure Q1/2, measure L, and compare this value. And because of the fact it's 1 millihenry and not 10 millihenries, the frequency at which you do this experiment in part 2 can't be 500 hertz. You got to set the frequency to 5,000 hertz. Set the frequency of the signal generator to 5,000 hertz. Otherwise, it's going to be very difficult to do the measurement. Because you're going to have to spread the signal out as much as you can. With 1 millihenries, the signal doesn't drop very fast. And so you have to spread the signal out as much as you can. And so you need to be able to set it to 5,000 hertz to be able to do that. Okay. I was fiddling around with this last night. I figured it's the best number. In fact, I actually kind of made some corrections to the lab. I will send you the corrections to it. Okay, I've made a correction. It's going to email you the updated version of the lab. Questions so far?
So for the smaller the inductance, the longer it takes to drop the voltage, I guess. That's true, correct?
The smaller it is?
Or sorry, the faster. Okay, I see. So I'm just trying to conceptually think about this. So the inductance or the inductor impedes the resistor's ability to dissipate energy. Is that correct?
You know what you're saying sounds correct, but L is it measures. It's a measure of the opposition to a changing current. But you're right, though. It does make it longer for the current to build up. I mean, the way you said it is correct.
Okay.
Okay, but in reality, it's a L is a measure of opposition to a changing current. But it takes the resistor a longer time to dissipate the energy. It takes a longer time to build up the current. So the smaller L is, the faster the current will build up. And the faster you'll either go up to T1/2 or go down. It depends on which part of the cycle you're looking at. You're looking at this part or this part. You're going to be looking at both of them at the same time. It doesn't matter whether you're looking at whether this thing charges, not charges up, but when it builds up, because your signal will look like this. So whether you look at this part or this part, it doesn't matter. Make sense?
Yeah.
And so the bigger L is, which I wish it was in our case, then this would be steeper. It would actually make the measurement for you a little bit easier. So I don't expect spectacular results for this one. That's our fault because we gave you a different... we were trying to choose one inductor for both the last two labs. And we shouldn't have done that because the inductors aren't that expensive. We should have just had one inductor for this lab and one inductor for the other lab. The last lab, 1 millihenry is okay. But for this lab, using 1 millihenry with this scope is tough to deal with. Because these scopes aren't that fast. Okay. Now, one of the other things, when I originally wrote this lab, I had assumed that we were going to get a multimeter that could not measure capacitance. However, these multimeters that we have, these multimeters can measure capacitance. Okay, this particular one, there's a this guy right here. I don't know if you can see it at the bottom. There's a scale for a capacitance. So you can actually measure the capacitance of that capacitor. Now that capacitor is polarized, so it'll say on it which side's positive, which one's negative. So make sure you hook it up correctly. My guess, if you hook it up backwards, you probably won't damage it because you're not putting a large voltage across it, but usually if you do, they'll pop. But this one shouldn't, because you're not going to put a large voltage across it. Okay, so you can, instead of using the label, in the lab it says you're going to compare the measured capacitance to the labeled value. I mean, you have the ability to measure it, just measure it. Because the labeled value a lot of times is not that good. The labeled value sometimes could be off by 20%, especially for this type of capacitor that we're using. So if you want to maybe make your results look good, you probably want to measure the capacitance. Now, measuring the inductance costs, getting a meter that measures inductance costs a lot. So neither of our meters, if I remember correctly, can measure inductance. That's an expensive feature to add on these systems. So for the inductance, you just got to go by this value, okay, by the color code. How good that number is? Well, it's probably 5% tolerance. It's that number plus or minus 5%. You probably won't get within 5%. And the reason being is the scope. We can't spread the signal that much. I expect you to be within 15% in part 2. Okay? Just because of the fact we cannot spread the signal out and because of the value of L we gave you. Questions? Okay. So let me show you. Let's focus in on the circuit. And I'm showing you the circuit with the scope you're using. I don't like this, and the reason why I don't like it because it just shows the input voltage. Okay, so if I were doing the measurement, what would I do to make this as accurate as possible? So first of all, I would want to make the signal as big as possible. So I'm going to actually move this signal up a little bit. So I'm actually shifting the signal up as I'm doing this. You press the volts per division button twice so you can actually shift it up. Okay, there's the bottom of it. And then I'm going to press the seconds per division button twice so I can actually shift the signal over in one direction. That writing is annoying. Now give me a second. This is so slow, but that's what you get for $20. But notice it's shifting over slowly. And I'm going to adjust the voltage until this takes essentially the whole screen. Oops, I didn't want to do that. A little bit more. So I adjusted the voltage until it takes about the whole screen. So Basically, half the voltage is right along the x-axis. You see what I'm doing? And then let me use the best scale here. And I'm doing this one. This is with the inductor. I have it set to 5,000 hertz. And now I can measure how much time it takes for the voltage to go to half its maximum value. In fact, all I got to do is measure the time it takes to get to this point. The horizontal distance tells me the time. In fact, I can freeze this. So that way the measurement's steady. Okay? So those are the things I expect you to be able to do with the scope. I want you to be able to play around with the scope so that you can actually make the measurement, the time measurement. So you're measuring the time it takes. Notice what I did. I put the transition right along the y-axis. Where the transition occurs is right along the y-axis. And I made a signal big enough so that V1 half occurs right along the x-axis. Okay? I know this is the maximum value, that's the minimum value. And then I just got to measure along the x-axis, I can measure the time. That's really all I have to do, so it's pretty straightforward. I just got to play around with the scope. And I can freeze and unfreeze the signal. Okay? That's what I expect you to do for the 3 measurements you do for the capacitor and the 1 measurement you do for the RL circuit. So let me show you the RL circuit quickly before I destroy it. See that big looking resistor? You see a big resistor and a little resistor. Actually, the big resistor is the inductor. There's another big resistor in your circuit. That's for the last lab. That's an actually 1.2 ohm resistor. But this is the inductor that you'll be using. Please let me know if you don't have it. Let me know right away. Okay, so we can get you one. Okay? The resistor you'll use is 100 ohms. I wish I had a smaller resistor, but that's all we got. Okay? So that's the RL circuit. So what I want to try to do is I want to show you my other scope. I want to do this with my other scope because I have an RL. This was the RL circuit I had the other day, and there was an issue I had with the wiring, so I couldn't show you both signals. So I want to be able to show you both signals today. Okay. So let me show you the other case. So I'm going to remove this guy. Let me put the other one in place. And this one is different. Of course, you didn't get this one. This was the fancier one. This is my old version. I gotta plug this one in. Okay. Now I need to disconnect my other scope. Sorry for my hand being in the way. Now you can compare the voltage, input and output voltage. You guys see that? This is what I like about this. Is really the scope you should be using. So this scope shows you the input and the output voltage. So I can actually spread this out. You can actually see the decay of the signal, can't you? Okay, and again, this was the RL circuit. This is the RL circuit I had the other day. I couldn't show you the other display. Okay, and then the circuit is like right back here, which is hard to see. I can raise it a little bit. Okay, yeah, it's way back. It's behind here, unfortunately. There's the resistor. Okay. Any questions on this? Unfortunately, this scope costs $80. So it was hard to include this in the kit, and the school doesn't really trust the company that sells this. Okay, so unfortunately, we're stuck with the one input scope. Questions, concerns?
So the yellow one is without the inductor?
Yeah, the yellow one's directly from the power supply.
Oh, okay.
And then the orange one is with the inductor.
And, is this is AC current or is this DC current?
This is a square pulse.
Oh, okay.
So,
okay.
It just turns on and off. Yeah, I mean, I can set this to AC, but you won't notice that. All you'll notice is the phase shift. Let me try that. You see a slight phase shift. And when we start talking about this in the next chapter, you'll see the phase shift. Let me change this. Right, it's a very slight phase shift.
So with AC current, an inductor doesn't really do anything? Is that?
No, it does. You'll see a phase shift. Let me see if I can change. I'm changing the inductance. You see the phase shifting?
Oh, okay. Yeah, it gets squished, I guess.
Excuse me. Yeah, so it does get smaller in amplitude. And the amplitude does change when I change the, hold on a second. Let me see what else I can do. Right now I have it set to 1 millihenry, so it doesn't do much. But you can see it starts shifting as I increase the inductance. Okay. And then one thing I have this one hooked up to a box where I can change the inductance. So in this particular case, if I change the inductance, you can see the steepness change. This is 1 millihenry. You can even see the steep. You can't see it bending, right? And unfortunately, I might have to freeze this. Sorry. I have to remember the two scopes behave differently. There. So I froze it. Now if I change the inductance and I freeze it, and let me change the signal. 1 second. Notice how it bends more over here. If I make it even higher, look at how it decays faster. The slope is greater when I make L bigger. Okay? So unfortunately, in part 2 of your lab, L is really small. Right now, this is set to 52 millihenries. The one you have is 1 millihenry. So this is not going to be very steep. Okay? Well, what's nice about the 2-channel one is you can compare the power supply to the voltage across the inductor or the resistor. In fact, I have it hooked up across the resistor. if you have it hooked up across the inductor, the voltage looks more like this. It just spikes up. It does that. Okay. So if you have a hard time with this, with the inductor, then just look at it across the resistor in part 2. Okay. So I still want to talk about RLC circuits for a power supply that either is a square function or a battery. Okay? And the reason I want to talk about this is because you're going to see problems like this. Look, you probably see problems like this in other fields of physics. Those of you who take 215 next semester, you will see a very similar problem. Basically, the math is the same. The math doesn't care, right? As long as the form of the equation is the same, the solution will be the same. So, that's why I like talking about this. Now, I ought to warn you that normally a problem like this is covered in Math 33. But I'm going to use techniques. And I'm not going to go solve it in detail. I'm only interested in the behavior of the circuit. When you do Math 33, you'll go into more details. So I'm going to use a different technique maybe that you would be taught in Math 33. I'm not going to be rigorous when I describe the problem or solve the problem. I'm really looking for the physics. So suppose I have a power supply. I have a resistor, a capacitor, and an inductor in series. And I have a switch. Okay. Now, if I don't have a switch, then what I would use... On my computer? Hold on a second. Let me unplug my other computer here. My scope. Okay. Anyway, so this is R, this is C, and this is L. And we'll call this delta V. I close the switch and something will happen. I mean, I know what's going to happen, right? You'll get the current build up. And what happens as t goes to infinity? What should happen to the circuit?
It becomes an open wire because the capacitor is fully charged.
Okay, so initially you're going to have zero current. At the end, you're going to have zero current because this thing will be fully charged, right? At the beginning, this thing is going to cause the current to build up slowly. And so you're not going to get a spike. You're just going to get something like this. You're going to get something like this, and then eventually it's going to go down to zero, right? That's what you expect to happen. Okay, and this is taking out energy from the system. Without this, without this thing, energy will just go between these two. But this guy's taking energy out of the system. Okay. So we want to look at what happens as a function of time. We want to see the response of the circuit when I flip the switch. Or I want to see the response of the circuit when I put in a pulse like this, which is the same thing as if I open and close the switch repeatedly. Okay, the electronics can do it much faster than you can. Okay. So I'm going to use the modified version of Kirchhoff's laws and say, okay, the sum of the voltage drops is going to be 0. And the reason why I'm doing this is because it's faster. And I'm saying the current is going this way, so I'm summing voltage in that direction. So I'm going to look at the response of my circuit. And I'm interested in the current. I mean, sometimes people are interested in the charge in the circuit as a function of time. I'm really interested in the current. And so I know that, and most people don't solve problems for that. I know that the derivative of this gives me the current. Right? So why don't I, just for fun, take the derivative of the above equation? What do I get? Well, what happens to this guy when I take the time derivative? It's the power supply. What happens to it?
It goes to.
It's a
Wait, is
constant.
it 0?
It's 0.
Yeah.
So I get this is just I.
Why is Q just I?
Well, dq dt is I, right?
Oh, I see. Yeah.
Taking
Okay.
time derivatives. Now, there's all these minus signs. I hate all the minus signs because they multiply through by -1. Just give me a second. Just give me 1 second. Okay. Let me divide both. Let me cancel out the minus signs. And I'm going to divide both sides by L. Let me rearrange this. Divide by L. And so when I do this, I get the following. And I'm going to solve this. Okay? This is a Math 33 problem. But what do I know? I know that the current, I'm going to do this and decay to 0. From experience, I know that. So what if I say I as a function of time equals A e to the omega t? Let me guess that. So I'm going to guess. I'm going to guess that solution. Okay? I can do that, right? It's not the best way of solving a differential equation, but I'm going to guess the solution. I'm going to do something like this in the next lab too. Okay, when the circuit is driven by a power supply that varies with time. The other thing too, the other reason why I'm solving for I as a function of time instead of V as a function of time, I can get to my answers faster. Because otherwise, if I solve this, I got to think of 2 solutions instead of 1 here. So I'm going to take this and put it into the equation. So I'm going to do a couple of things fairly quickly. I hope you see what I ended up doing. When I differentiate this, don't I get 2 omegas out of it? I'm going to take the derivative twice, so I get 2 omegas out of it. And the same function I started with. When I take the derivative of this with respect to time, I get an omega out of it, plus the same function. And in fact, I'm going to eventually be able to pull out the function. In fact, I'll get the following. So this equation will always be 0 as long as the thing in the bracket's always 0. So basically all I got to do is find the conditions on this omega, find the conditions on this guy, so that I get 0. I just got to use the quadratic formula. Well, if I use the quadratic formula, you guys are all familiar with it, you're going to get minus b plus or minus the square root of b squared minus 4ac all over 2a. So my two solutions then look like this. I forgot a minus sign, you guys can catch that. Does everyone see that? But there's two solutions. So there's got to be 2 terms to this thing. So I really should write it like this. Where A and B are determined by the initial conditions of the circuit. Okay, A and B are determined by the initial conditions of the circuit. I'm not really interested in those. I'm really interested in the behavior of the circuit. Okay, remember omega 1 is this guy and omega 2 is this guy. But both of them have this term in it. Because of the fact that I have a radical here and here, there's actually 3 cases I have to deal with. There's one case where this is bigger than this. There's another case where these 2 guys are equal to each other. And there's another case where the second term under the radical is bigger than the first term, so we need to look at that. Let me see how am I doing with time. Okay, so first case, let's have and we call this overdamped. And so this stuff under the radical is positive. So I'm going to explicitly write this with the omegas, and it's going to look ugly. Sorry. And because both terms have this guy in it, let me write it this way. These equations come into play, for example, when you talk about the mass and spring problem, where you have air resistance, not air resistance, but we have resistive forces acting on it. You get the same solution. Like if you're designing shock absorbers, okay, you get a similar equation to solve. And so this is called overdamped. And what happens is, when you plot I as a function of t, current builds up and then decays exponentially with no oscillations. Okay? So you get an exponential decay with no oscillations.
Professor?
Yeah.
The E outside the brackets and the E's inside the brackets, they both have T's. Was that?
Yes, because.
T squared.
Right? Should they have T's in them?
I don't know.
Yeah, it's this, right?
Oh, okay. Okay.
Yeah, it's important to have those. I mean, those T's are important. So the signal decays without any oscillations. This exponent is so this exponent is negative, this exponent is positive, and this is negative. Okay, so basically what happens is you do get, because of this term, the signal doesn't decay as fast as it should. Now there's another case where R over 2L squared equals 1 over LC. Now what happens in that case? Then if that's the case, then what happens to this term?
It goes to 0.
It goes to 0. But here's, so then I looks like this.
It should just be A. I equals to A, or B, or...
Yeah, there's something we have to consider. Well, I don't want to spend time doing the considerations. So this is 0, right? That's it, right? But then the second term, there's actually, writing this is the same solution, just writing A, right? There's got to be two solutions. Because of the fact that I'm taking the second derivative, there's got to be two, and there's got to be involving two constants of integration. So one can go through the math. I'm not going to do that here. I'm just going to tell you that you can write it this way. This is another solution to the equation. And this represents the fastest time it takes for the system to reach steady state. So, reach a steady state. Or, I shouldn't say reaches, but approaches steady state. And the fastest time curve. Very difficult to actually observe a system like this, but they can happen. This is called critically damped. And you will talk about this next semester when you take Harris's class, except for the mass and spring problem. Okay, you'll see the same thing. The last one, this is the fun one. Guess what? It's the last condition. The last possibility. What happens there? Anybody want to guess what happens there?
Imaginary numbers.
Yeah, I got imaginary numbers. So I actually have to rewrite the exponent the following way. Because I have to factor out the square root of -1. What's the square root of -1? I, okay. I'm also going to write I hat. It's not an I hat. So this is your other solution. And of course, if you're familiar with Euler's formula, you guys familiar with Euler's formula?
I don't have it memorized.
That's Euler's formula. You can write this in the following manner. And again, A and B are determined by our initial conditions. Oh no. This is going to take a lot of space. I forgot my T. I forgot my T's here. So, what does that represent? What's the current do as a function of time? It's too far down. I'll draw it here. Builds up, and then slowly decays to 0. So I did this lab over the summer. So I want to show you what it looks like. Okay, so I'm going to that's what it looks like. Oh, Daniel, I'm sorry, I missed what you wrote down. Means it's the first term. Where was that in reference to? Oh, the create Lagrange. Okay. Yeah, there's actually, yeah, eventually you can show that that second term exists. You can write that, and I don't want to go through the math. It's math 33. So that's what it should look like. This is what I was expecting to do for part 3. Well, we can't do it because the L is too small. Okay, so you guys see that damping? Oops. Uh-oh, I think my video froze. Just give me a second. Oh, I think I'm okay. All right, sorry about that. Yeah, so that's what that happens. You do get oscillation, and so this is called underdamped. This one's called the critically damped case, where one can show this extra term in the solution. I don't want to go through it here. Okay, and then this is called the overdamped case. Those are 3 cases you get. And then when you talk about the mass and spring problem with air resistance, or if it's in a fluid with some sort of damping factor, you get the same thing. And so in this particular case, the damping is represented by the resistor. The resistor actually damps out the system. If I just had a battery, then this is what you would observe. So if I had a power supply that varies the time of square pulse, then you would see this repeated, like you see in that figure on the scope. Okay. If you were to plot, if you would actually solve for Q, in other words, you would integrate this, equation, or you would actually take my equation that I originally had and either solve for V or for Q. Then your graph, if you plot it as a function of time, you get the following. Let me show you the graph. Oops. It takes a while to change screens. So that's what you would observe. If you're actually solving for capacitor voltage as a function of time, you would actually get that expression. Where you have when you have an underdamped case, then you get oscillations about the maximum voltage of the capacitor or the power supply voltage. Yes, Daniel, sorry, I missed your question. Yeah, the case for the critically damped case is just the first graph, but yeah, it gets to the steady state faster. You're correct about that. So when you see the graph on the screen, that you see on the screen right now, the green dotted one is the critically damped one, and it reaches the steady state case fastest. Because you just have, both terms have a negative exponential, right? Because in the case of the overdamped case, this negative exponential is competing with this guy, which is a positive exponent, right? In this case, you don't have that here. You just have this full R over 2LT. Then you have, in the case of the critically damped, the overdamped case, you have this guy with the positive exponent. So it's not going to decay as fast. So yeah, you'll reach steady state in the shortest time period in the critically damped case. Other questions? Okay, just quickly, I wanted to talk about the case where you don't have the resistor in the circuit. Let me go back. Oops. Suppose we have a circuit, suppose we have a circuit with just a capacitor and an inductor. Maybe let me set this up so because otherwise that figure is kind of confusing. Suppose I have something like this. Power supply, switch, capacitor, and then an inductor. I close the switch, capacitor charges up. Once it's charged up, I open the switch. Okay? Let's set that, that's the scenario I'm setting up. So what happens? The capacitor charges, there's no resistance in the circuit, okay? The capacitor charges up. Once it's charged up and you open that switch, the capacitor is going to want to discharge through the inductor. Because the inductor opposes the change in current. And so basically what happens is the current is going to slowly decay off to zero. So all the energy that's stored in the capacitor, it goes into the inductor. Once the inductor has maximum energy stored, the energy is going to go back into the capacitor. Remember, there's no resistance, so there's no energy lost. We're assuming no energy loss is either due to accelerated charged particles, radiation, okay, or resistance. It's idealized. And so basically, you have a system like a mass on a spring. You're converting kinetic energy and potential energy. Similar to that. So your total energy in your circuit at any time is the energy stored in the capacitor plus the energy stored in the inductor. If I take a time derivative of this thing, since energy is conserved, I have no energy losses, the derivative of this function with respect to time is zero. If you have a resistor in your circuit and you took the derivative of this with respect to time, then what you would get is I squared R, which is what we have for the LRC circuit that I drew. So basically I have, if I take the time derivative of this, d2q dt is going to be q dq. And then the derivative of the current, is going, the derivative I squared is going to give you I di dt. Because remember, I is a function of time, and q is a function of time. And also remember, like what I did up there, I is dq dt, and di dt is the second derivative of the charge with respect to time. Okay? Di dt is the second derivative of q with respect to time, and I is the time derivative of q. So that means then, I can write this in terms of just q's. And I can solve for q. But actually, if I wanted to, I can write this in terms of I and solve for I too. But let's solve for q. So when you take a look at that equation, it says I take the second derivative of the charge with respect to time, and it's equal to some constant times q. Basically, I'm taking the second derivative of a function, and I'm getting the function back times a constant. I need to figure out what function does this. This is one of those problems where I just can't integrate twice because I don't know q is a function of time. I actually have to figure out what q is. This is a Math 33 problem. However, you folks, I think, have a little bit of intuition as to if I take the derivative of a function twice and get the same function back times the negative of a constant, what function would that be? Can you guys tell me? Yeah, it's sine or cosine. If you take the derivative of sine or cosine with respect to time twice, you get the sine or cosine back times a constant, a minus sign. And so we can write the function this way. By the way, there's two ways to write the function. Let me write it on the board. There's two ways to write the solution, and they're completely equivalent. I can write Q like this. Okay? Actually, there's more than two ways. This is a constant of integration, this is a constant of integration. Or I could write it like this. They're equivalent. I can write it a different way too. I can do it this way. Well, I won't do it that way. I can write it in terms of complex exponentials, but I won't do it that way. Okay. I can make this a sign also. I could put a minus sign there too. So there's a lot of ways to write it. But in the end, they're all equivalent. All you got to do is relate the constants of integration to each other, and you'll see that they're the same. So omega squared ends up being 1 over LC, which is characteristic of what we had in this equation. That 1 over LC pops into here too. Okay, that's actually, turns out, that's the frequency at which the circuit wants to oscillate. We'll see that in the next chapter. Okay. So remember, we had this equation. Okay, so I take a derivative twice and I get this thing coming out. So I wrote my omega as the square root of 1 over LC. Because if you take the derivative of this thing twice, omega comes out twice, so get the 1 over LC out of it. That's where you get this relationship. We call that the angular frequency. And then the derivative of the function with respect to time just gives you a sine function. And so to determine delta and determine Q, all I got to do is know what are my initial conditions. Based on my initial conditions, I can get Qm and delta. Those are my constants of integration. And I avoided doing that in the RLC circuit because I was only interested in behavior. But let's look at it here. Can we figure out delta and Q max? Well, let's assume that Q equals Q max and I equals 0 at T equals 0, which is the system I set up in the picture. Well, look. If I plug in T equals 0 here, okay, and I said Q is Q max, I get that. I need to write this. What must delta be? What's the most obvious choice for delta?
0.
0. Right. Yeah, I can put 2 pi in there, but that's fine. I'll just choose 0. So Q equal Qm cosine omega t. So what about I? Oops. What about I? So I is the derivative with respect to time. We know it's 0, so notice when t equals 0, this whole thing is 0. So this is I max. That's when t is equal to when omega t is equal to pi over 2. All right. This is the current when omega t is pi over 2 or 3 pi over 2, etc. And the negative sign just tells you that the current and the charge are 90 degrees out of phase. We're going to be looking at signals, things where the functions are out of phase. What does out of phase mean? That's a term you're going to have to learn. What does out of phase mean? Anybody want to guess?
Well, it's a shift in, like, the graph, I guess.
Yeah, you're right. There's shifts in the graph. The peaks don't come at the same time, right? The peaks in the two functions don't occur at the same time. They're shifted, right? So if you have a if you have like a sinusoidal function, this is the phase. Basically, the angle that you're at is the phase of the function. And so if you have two functions whose peaks occur at different phases, this is called a phase difference. So get used to hearing that term, because in this course, especially in 215, when you talk about waves, that term phase difference is very important. Because this basically a shift in angle between two peaks. That's the phase difference.
What is omega again?
Omega is the square root of 1 over LC. It's called the angular frequency.
Called the what? Sorry.
It's called the angular frequency.
Oh, okay.
Right. It has units of radians per second. Do you remember angular velocity?
Yeah.
Yeah, this is just radians per second, but we call it angular frequency because this is related to 2 pi f. We'll use the term angular frequency because when you do problems in physics 215, you need to know the difference between angular velocity and angular frequency. They're confusing. Okay, you do a pendulum problem to see what I mean when you take 215 next semester. Okay, and I'm sorry, I'm going a little bit over. Just let me say a couple more things about the LC circuit. Some folks spend a lot of time on these. So again, the total energy is the voltage, the energy stored in the capacitor, and the energy stored in the inductor. And so what happens is in the LC circuit, energy is transformed or is transferred between the inductor and the capacitor in the circuit. And if there was a resistor in the circuit, the resistor would be taking away some of that energy, would be dissipating that energy. Okay. And so when you add R in your circuit, when you add the resistance in your circuit, this causes the energy to be dissipated. This factor here. And so when you take the total derivative of u as a function of time, it's not going to be 0. It's going to be I squared R. If you wrote Kirchhoff's, you applied Kirchhoff's law and then multiplied by the current, and then took a derivative, your du dt would be bi squared r. It's because the resistor dissipates all the energy. Any questions? All right, so we're actually done with chapter 32. We're really at a good pace in this course with our group. So Friday is our exam. All right, and I know we're going to kind of have to keep up with the homework. So I don't expect you to have started the homework already in chapter 32 because you're getting ready for the exam. Okay. By the way, my other class was taking the exam today. And so as they were taking the exam, I was grading your retakes. I apologize why it's taking me so long. Okay, but I'll get them done today. All right. No questions or concerns?
None for me.
Okay, so then we'll see you on Friday. Good luck. Hopefully I'll see you in office hours if you have questions, or just email me. And my goal this week is to try to catch up on grading. Because when I have a day off, we have a day off Wednesday. All right, take care.
All right, see ya.